Hey guys, welcome. Yeah, so hopefully you've watched my more basic example on Laplace transforms, which is for the function f of t equals a, so for the constant function. But yeah, in this video, as per promise, I'm going to do the Laplace transform for f of t equals a times t. Yeah? Okay, cool. Now, by definition, then L of a times t is going to equal, well, its other name is capital F of s, and it's going to equal the integral from 0 to infinity of e to the negative st times at times dt, right? Okay, cool. And next, we know that we can take out this constant, write it in front of the integral, so I'll do that. And write that what we have is the same as a times integral from 0 to infinity of t times e to the negative st dt, right? Okay, cool. Now, since this is an improper integral, just like we did in the first example, we will have to rewrite limit as b goes to infinity, the integral from 0 to b t times e to the negative st and then dt. Yeah? Okay, cool. Now, to deal with this integral here, we just have to do integration by parts. And so then we're going to say that u is equal to t, so du is equal to dt, and then dv will have to be equal to e to the negative st dt. So v will then have to be negative 1 over s times e to the negative st. Yeah? Okay, cool. So then we come back here, right, and write that what we have is the same as a times limit as b goes to infinity of what? Of, now we can figure out what this antiderivative is, and it's uv, so t times negative 1 over s times e to the negative st. And if we simplify all of that, it's going to say minus t over s, and then in the denominator, e to the st right here. Yeah, okay, cool. That's uv. And then minus, and then v du, right? So v comes with a negative, so that'll turn that into a plus here. And du is just dt, so plus. And then I could also factor out the 1 over s from the v. I've already taken care of the negative and changing the minus sign that comes from the integration by parts formula into a plus because of that negative. Anyway, I factor out at 1 over s, and then I could write the rest of what I have to write as, and by the way, I have to write 0 and b here because we have to evaluate, right? Okay, cool. And then I write 0 and b here, and then v du, right? So the rest of v is e to the negative st, and then du is just dt, nice. And there we are. Yeah, okay, so this is what we've got so far. Cool. Now, the antiderivative of e to the negative st is just negative 1 over s e to the negative st, as we've already said. So what I've got is the same as a times, and then it's lim as b goes to infinity of, well, I guess we can evaluate in this part. So plug in b, so you get negative b over, and then it's s e to the sb, and then since we are evaluating, we have to write minus and then plug in 0, so we just get minus 0 over s, but that's 0, so minus 0, okay? And then plus 1 over s times the antiderivative here, and evaluated will be negative 1 over s e to the negative st evaluated at 0 and b, right? Okay, cool. All right. So next, I have enough space. Next, we can write the following, which is a times and limit as b goes to infinity. And here I just have negative b over s e to the sb. And then we have here, what are we going to get? Well, we have plus 1 over s times, when we plug in b, we get negative 1. Well, I guess that'll mean this will have to change into a minus, but it's fine. But negative 1 over s, and then e to the negative SB, but we can write that in the denominator as just e to the SB with a positive exponent, right? Okay, and then we'll have to write minus, and then it's going to be plugging in 0. E to the 0 is 1, so we have minus, and then it's negative 1 over s. This minus sign is from the evaluation theorem in calculus, right? Okay, cool. And do I have sufficient parentheses? No. We have this parenthesis we opened that we need to close. Okay, cool. So, finally, finalement, we have a times, and then its limit as b goes to infinity of negative b over s times e to the sb, and distribute the 1 over s. Here we're going to get minus 1 over s squared e to the sb, and then distribute it over here, and notice minus minus is going to be plus, so plus 1 over s squared, right? Okay, cool. Now, as we send b to infinity, notice that e to the sb is going to outgrow negative b here, or just b here. So if you just ignore the negative sign for a second and look at the quotient b over s times e to the sb, as b goes to infinity, e to the sb is going to way outgrow just b, right? And therefore, this is going to go to 0. And then here, the denominator, again, is going to dominate the numerator, which is a constant 1, as b goes to infinity. So this goes to 0. So what we have is just equal to a times, once we've sent b to infinity, we just have a times 1 over s squared, which is a over s squared. So it turns out that the Laplace transform for the function at is a over s squared. Yeah? Okay, cool. This is it for this video, but in subsequent videos, I'm gonna do e to the at, and then sine at, and then cosine at. So keep watching. Take care.